minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff.
The tower.
Roger, tower clear. We're getting a roll program.
After hundreds of years of dreaming about it, we're finally able to really leave our planet and travel into space. We know how Earth looks from space. We know how the moon and many of the planets look up close. We've seen our Milky Way and neighboring galaxies in ways we've never seen them before, from instruments in space. When we leave Earth, when can we say we're in space? Well, we can say that space begins where our atmosphere is too thin to have much effect on things that are moving through it. This is at an altitude of about 60 miles, or 100 kilometers. Space begins here, and then we divide it. Space between Earth and Moon is cislunar space. That's a circle with a radius of about 400,000 kilometers. About 65,000 kilometers from the Moon, lunar space begins. This is where the Moon's gravity becomes stronger than the Earth's. Interplanetary space is all the space the planets move through. It's also called solar space because the sun is the most important gravitational influence here. Interstellar space lies between the stars of our galaxy. And intergalactic space lies between the galaxies. Now, to get into space, you first have to overcome the Earth's gravity. It's easy to do that. You overcome gravity every time you throw a ball. Gravity and air resistance slow the ball until it stops rising. Then gravity pulls it back to Earth. You can make a ball go higher by throwing it with more force. The more force you use, the higher an object will go. You can shoot an arrow much higher than you can throw a ball. You can shoot a bullet higher than an arrow. And a jet will go even higher than a bullet because the great force that propels it is continuous. A jet engine depends on air, but rockets can operate beyond the atmosphere where there is no air. In other words, in space. Rocket engines supply the large continuous force that's needed to overcome gravity for space travel. I can show you what happens to these space vehicles. Let's suppose this saucer represents space, and this metal ball represents a space vehicle. Now, some space vehicles rise into space and then fall back to Earth again. Some stay in space, but follow a path or orbit around the Earth like Skylab does. And some escape the Earth like the Mariner probes to Jupiter and Saturn. But let's start with the vehicles that fall back to Earth. Here's a rocket almost ready to be launched. The final fueling and checking of all the important parts of the rocket is nearly completed. This is the countdown. Nearby are the scientists and technicians who direct the countdown and monitor the flight of the rocket.
4, 3, 2, 1. Fire.
Now the fuel begins burning in the rocket engine. Hot gases rush out of its tail, and the rocket begins to rise. Let's see why. The same force that pushes the gases down out of the rocket pushes up on the inside of the rocket. This upward force is called thrust. If the thrust is great enough, it will push the rocket into space. As the rocket rises, its speed keeps increasing. We say the rocket is accelerating. We can see what happens to an astronaut riding an accelerating rocket by imagining him in an elevator and on a scale. The elevator will provide the acceleration, and the scale will show its effects. Before the elevator starts, our astronaut weighs 157 pounds, or 71 kilograms. The weight is caused by the force of gravity. Watch what happens now as we start moving the elevator up, and its motion accelerates, going from 0 to a maximum speed. We'll stop the film while the elevator is still accelerating. Now, notice the astronaut's weight. It's increased from 157 pounds to 259 pounds, or 117 kilograms. That's because the force that causes the acceleration upward also causes an opposite force that pushes downward on the astronaut. This downward force acts like the force of gravity, so it's called a G-force, or gravity force. If the astronaut's weight had doubled, we would say that he was undergoing 2 Gs. During a rocket launching, a space traveler might undergo forces of up to 14 Gs as the rocket accelerates to thousands of kilometers per hour. After its fuel is used up, the rocket continues coasting into space. If the rocket is traveling less than about 30,000 kilometers per hour, the pull of gravity will gradually slow the rocket until it stops rising. Then gravity pulls the rocket back toward Earth again. The rocket leaves space and re-enters the dense part of the atmosphere. As its speed increases, friction with the air makes it get very hot. This heat of re-entry can destroy an object unless it's built to withstand extremely high temperatures. Now, an object will stay in orbit around the Earth if it has the proper speed and direction, the proper velocity. This rocket will place an object into orbit. The rocket is actually composed of several sections or stages. Each stage of a rocket can be powered by one or more rocket engines. At the top, a nose cone protects the satellite. Many satellites, like this one, are now in space, orbiting the Earth. They're called artificial Earth satellites because they travel around the Earth like the Moon does. The Moon is the Earth's natural satellite. For you to see how a satellite goes into orbit, let me use the metal ball and the saucer again. You can see that with a little push, the ball goes up a short distance and falls back to Earth. Now, the harder I push the ball, the farther it travels before it falls to Earth. This time it went nearly halfway around. I can make the ball travel all the way around several times by giving it a sideways motion and a high enough velocity. Now the ball is in orbit. The velocity required for an object to stay in orbit is called orbital velocity. For an object within a few hundred kilometers of the Earth, orbital velocity is about 30,000 kilometers per hour. A rocket that places a satellite into orbit at first rises directly upward. But the direction has to change for the satellite to go into orbit. There are different ways to change the direction of a rocket in flight. Sometimes small rockets attached to the main rocket do it. When one of the small rockets fires, that changes the direction of the main rocket. Another way to change a rocket's direction is to have a pivotal engine. When the engine tilts in one direction, that moves the tail of the rocket in the opposite direction. After a while, All the fuel in the first stage of the rocket is used up. Now the first stage falls away, and the next stage begins operating. Each stage increases the satellite's speed until the satellite is traveling at orbital velocity and moving nearly parallel to the surface of the Earth. Then the nose cone separates from the last stage and splits apart. Then the satellite is released. Now let's stop the ball and the saucer here. If it weren't for the Earth's gravity, a satellite's motion would carry it in a straight line away from the Earth. But because gravity pulls the satellite down toward the center of the Earth, the satellite instead follows a curved path around the Earth. As long as the satellite has the proper velocity, the force of gravity will hold it in orbit, but won't be great enough to pull the satellite back to Earth. The orbit is a closed curve called an ellipse. At this point along the elliptical orbit, the ball has reached its farthest point from Earth. This point is called a satellite's apogee. The point at which a satellite is closest to Earth is called its perigee. As a satellite travels in orbit, it appears to have no weight. To see why, let's look at our elevator astronaut again. Now at the top floor of the building, his weight is again about 157 pounds, or 71 kilograms. Now we're going down. As the elevator accelerates downward, watch what happens to the astronaut's weight. Let's stop the film here at 60 pounds, or 27 kilograms. If the elevator could be accelerated at the same rate as an object falling to Earth, then the scale would indicate that the astronaut's weight had dropped to zero. He would have entered a condition called weightlessness, or 0G. This is exactly the condition that an object is in as it orbits the Earth. Both the object and the people or things it carries are said to be weightless, as these astronauts are in Skylab in orbit around the Earth. A satellite will stay in orbit until friction between the satellite and the air slows its motion down below orbital velocity, and the satellite falls back to Earth. And now, for the space vehicles that leave Earth and don't necessarily come back. For a rocket to escape the Earth's gravitational pull, an engine must be used to give the rocket enough thrust to reach what is called escape velocity. That's about 40,000 kilometers per hour. At this velocity, an object will not go into orbit around the Earth. Instead, it will travel so far into space that other bodies of our solar system begin to exert a stronger gravitational influence than Earth does. By reaching escape velocity, rockets have already sent probes millions of kilometers into space. We've landed on the moon. We've seen the cratered surface of Mercury. We've orbited satellites around Venus, and we've landed instruments on its surface. We've mapped the surface of Mars from orbiting satellites. And with probes that have landed there, we've examined the red soil in a search for life. We've sent probes to Jupiter and on to Saturn. Escape velocity from the solar system itself is about 100,000 kilometers per hour. Once we achieve this velocity, we can send our instruments to other parts of our galaxy. We can reach the stars.